Okay, students, welcome to class number 9. Just we are going to the new topic called as signal flow graph or SFG. Now, we have already studied about block diagram. That is a way of pictorially represent a system. And in the block diagram representation, we have the components as the takeoff point, block, and summing point. Okay, now you can reduce the or you can simplify this pictorial representation by another type of representation called as a SFG. Now in SFG, to simplify, what happens, what we do is we will be, I mean, there will not be any blocks in summing point. The summing point and will be considered as a node, while the block, inside the block you have the transfer function. Generally that transfer function will be represented by a line connecting to nodes, and over which you will be writing the transfer function, which then we call this as the transmittance. So in short, in order to simplify block diagram, what we do is the block, the summing point, and the takeoff point will be replaced by nodes and transmittance in SFG. So there are only two components in SFG. One is nodes, the other one is the transmittance. Now let's see some examples of SFGs. Say for that, I'm just considering a closed loop, simple closed loop path, closed loop transfer function. That is a HFS, and you have a GFS here. This is a simple block diagram. We all know that is this is equal to CFS and RFS. Whose transfer function we know this as G by, say, suppose this is minus, this is 1 plus GH. Okay, assume this as H. Okay, so this is RFS, CFS by RFS. Now how to draw the signal flow graph of this? The signal, so this is actually the block diagram, so you need SFG of this. So how to draw this SFG? I told you that nodes will be the nodes here, no change, so this can be also gone. Now this is a summing point. Summing point can be considered as a node. Okay, so between the summing point and this node there is no value, it is just the RFS. Then between the summing point and you have an output node or a takeoff point, so that takeoff point can be considered as a node, and between this you have a transfer function, and in the SFG the transfer function will be replaced by the transmittance. It is just writing that G over that line, that's all. So then that becomes a transmittance, and then you have from this node to the summing point, this is considered to be the summing point node. Now that means there is a connection like this. Now you must specify the in SFG the arrow is so important, it's very important. So you will have to mark the arrow. The arrow suggests the direction of the signal from the input side to the output side. So this is your SFS. So once when a signal goes, it goes in this line and it comes over here. Now there is a feedback. So this is the feedback. No signal will be going through this, but the signal coming here may be fed back based on the value of this. Now what is the value of this? This is H. Now what type of feedback it is? It is minus. So there is no provision to put minus or plus. So what we do is we multiply that by that negative sign. Okay, so minus H will be this transmittance of this feedback path, right? Now when you look at this, you can see that there is a transmittance. There are transmitters. There is a forward path as well as a feedback path, and the forward path transmittance is G, feedback path transmittance is minus H. Okay, now look at this is an example of a simple SFG. So what you can see is you have you have 6 nodes: x1, x2, x3, x4, x5, and x6. In between x1 and x2, you have a transmittance of A. So we need to understand that there is a block whose transfer function is A. Then in between x2 and x3 is there another block which is having a b. Now from x3 there is a feedback going to x2, right? And that is marked as c, right? Then you have between x3 and x4 you have another transmittance d. E is called as another transmittance, g forward transmittance, while f is the feedback transmittance. So all these can be considered as this b, okay, d, the all these things are the transmittance, right? Now these are the transmittance, and while these things are called as the nodes. Okay, now what you need to do is the question is to find out x6 by x1. Now what is this x6 by x1? x6 by x6 is the, this is the output, right? x6 is the output, while this one x1 is the input. So, and assume that all these are in frequency domain. So what is x6 by x1? That is your transfer function. Now to find out the transfer function, what you need to do is to simplify the most from the, I'm actually explaining from the basics. So from the figure, see, you can write equations for each node, right? Now starting from there's, I mean, there's no equation for x1 anyway. Now you can have x2 equation for x2. What is this x2? x2 is a node where it's a node, look at it carefully. You are going to get two signals from two different sides. One is it comes from x1, so this is a times x1, right? But x2, as far as x2 is concerned, x1 is just a part of the signal. Another part is c times x3, right? So this is c times x3. Is it plus or minus? It is plus. Why? Because there is a plus sign in the transmittance. Then what about x4, x3? Now when you look at x3, it is actually b times x2. You don't have to consider this because it is a signal that comes away, that goes away from, that contributes to x2. Now for x3 at the x3 node, the only signal that comes in the forward path is from x2. That means it is x3 is equal to b times x2. Now what about x4? Now x4, when you look at x4 is contributed by two signals, two incoming signals. One is from x3, so that will be dx3, transmittance times x3 plus fx5, right? Now finally, when you come at x5, what is x5? x5 is equal to e times x4, while x6 is g times x5. Okay, now you have got a series of equations for node 2, node 3, node 4, node 5 and node 6, and what you need to do is you want to get the expression for x1 and x6. Now we know that coming to the second node equation, that's this equation. Now just compare with these two equations. This is the equation which consists of x1, and this is an equation which consists of x6, and we need a relationship between x6. So all the other things are just intermediate variables. We are only worried about x6 and x1. That means we need to eliminate all other things. Now how to eliminate this? Now elimination can be done by substitution as well, right? Now what you will get for x5 here? Now from this you will be getting, now let us call this as, say, call this as 1, this is 2. Okay, I will use another. This is 1, this one has 2, this one has 3, 4 and 5. Now from 5, now from 5 what you get is, from 5 we get as x6 is x5 is equal to x6 by g. So what you do is you are taking the last equation. We are not much concerned about x5, but so if it will be nice if you get x5 in terms of x6. Now substituting in 4. Now what is that? So this will be x6 by g is equal to e times x4, right? Right? Now what is x4 from this? Now from this you will be getting x4 to be x6 by g into e, right? Okay. Now you can substitute in 3. Now what all things you will substitute? You can substitute for x4 as well as x5. x5 we have already found in x6, so x4 is x6 by ge is equal to what is x4? D into d times what is x3? x3 we do not know, so just put x3 plus f into x5, and we know that x5 is x6 by g, right? So what you get is from this you will be able to get dx3 is equal to x6 by ge minus f times x6 by g. Okay, so you can take the LCM here, so you will be getting this as ge is equal to x6 minus minus fe x6, right? So that is your x3 dx3. So from this you will be getting x3 as dge, right? So now substituting this in the second equation, so this will be x6 minus fe into x6 by ge is equal to b times x2, right? B times x2, right? Now similarly you can do the substitution in x3 as well. This x2, from this you can evaluate x2. What is x2 here? x2 is equal to x6 minus fe into x6 divided by ge into b, right? This b comes over here. So you got x3 and x2. Now what about substituting in this x3 and x2? Okay, so substituting all these things in 1, what you get is, instead of x2 you will write this as x6 minus fe into x6 divided by g into b is equal to a times x1 plus c times x3. What is x3? x3 is x6 minus fe into x6 divided by ge, right? Now from this you can take you can bring all this x6 to one side, and you will be getting an x6 by x1. You may do it by yourself, x1, so that you will be getting this as a b c d g by 1 minus bc plus ef plus bc ef. Okay, so this is the answer that you will be getting after the substitution. Now what we did is, actually we went on to substitute towards in the back direction, right? x6 to x5, then x6 x5 to x4, x4 to x3, x3 to x2. Okay, now this method we call as the back substitution method. So what is the theory behind this? Get as many equations, get every node equations, and start back substituting until you arrive a total relationship only in terms of x1 and x6. And that's the logic, and take the ratio, you will be getting the transfer function. Okay, now the transfer function is given by a, b, e. It is not c. E into dg by 1 minus bc plus ef plus bc into ef. You may do the correction. So this is the correct reset. I mean, when you derive, you are going to get like this. I will rewrite it for you. The transfer function. The transfer function is given by a, b, e, d, and g. A, B, D, E, G, or A, B, E. It's not C. 1 minus BC plus EF into, plus BC, EF. Okay. Now let us have some interesting point just to generalize, just to think of generalizing this transfer function. Anyway, this back substitution method, this is what we have done so far is called as a back substitution method, as I mentioned earlier. Now, what is the problem with back substitution method? As the number of node increases, the equation that needs to get substituted gets complex, and you are more prone to commit error, right? So there must be some generalized way of assessing the transfer function from a given SFG. Now, we are in a move towards that. So to start with, I'm going to correlate the obtained. So anyway, this is going to be the transfer function. We have proved that the transfer function of this system is this. Now what is this A, B, E, D, G? When you look at this, the gains, this is the product of the transmittance of this one into this one, into this one, into this one, into this. So that means it is a product of the transmittance of what? Of a path that starts from x1 to x6. Now, the path, the signal travels from the input to the output side is what is called as a forward path. That is called as a forward path. So this A, B, D, let's call this as D into EG. A, B, this is E, E. This is not C, it is E. A, B, D into G is called as the forward path transmittance. Forward path transmittance. Hope you got what is this forward path. Now I'll just give you another example. See, consider this signal flow graph. Now, how many forward path this particular signal flow graph has? See, one way of going a signal, when a signal is passed, say X, it will reach at this point. It can reach at this point by two ways. One is directly to this, another way is this one. So that means this particular thing has got two forward path gains. So the forward path gains will be, say for example, if I am doing this as M, B, Z, D, E and F, what are the two forward path gains that you can have? That will be A, B, C, E and A, F, E, right? So these two represents the transmittance of a forward path. These are the forward path transmittances. Right? These are called as a forward path transmittances. Now, coming to this, so you can say that I'm going to generalize this. The transfer function is the forward path transmittance divided by 1 minus what is this? 1 minus the sum of some transmittance, that is BC and EF. And what is this BC? BC is actually a transmittance in a loop, right? You have a forward path and it goes in this way and reaches the same node. So the path from which the signal travels and reaches the same node is what is called, that path is called as a loop. So how many loops you have? You have 2 loops, right? So that means you have loop gain as well, or the loop transmittance. Now in this case the loop transmittances are BC and EF, or you call it as the loop gain. So you can call this as 1 plus the sum of loop gains taken individually. Okay, I'll explain why the term specifically I am saying individually. Now coming to the next one, that is 1 minus, then comes a plus BCEF. And what is again BCEF? BCEF is again the product of the loop transmittances. One transmittance is BC, other one is EF. So it is the product of BCEF, and we call it as the sum of, it will be, and anyway you have only one combination, so sum of loop gain non-touching. I am introducing a term, I will explain what it is. Sum of non-touching loop gains taken 2 at a time. So in this case you have only 2 non-touching loops, and there can be only one combination. Say for example, say in this case I am considering a signal flow graph something like this. Okay, so this is one loop, this is another loop, this is another loop, right? So how many loops you have? Say call this as A, B, C, D, E, F, G, H, I. How many loops? How many loop transmittance? You have A, B loop transmittance, D loop transmittance, and GH loop transmittance. Now what is the meaning of taken 2 at a time? So here also, in this case also, when you take the sum of the loop gain individually, you will have a term like this, ABD plus BG. Now what about 2 at a time? That means taking this loop together, then this loop together, then this and this. So you have 3 combinations. That means you will, in such case, you will be having 3 combinations, ABD, ABGH, and DGH, right? So it is the sum of the. Now what do you mean by non-touching loop gains? These loops are called to be non-touching because the nodes formed in the loops is not touching the loops, other loops. Now you can have a scenario like this, right? Say this is a loop, right? And you can have another loop like this. So what happens? This node is sharing 2 loops. So this is called as a touching loops, and you cannot consider when you take this 2 at a time. You can have individual transmittance, but when you take 2 at a time, that has to be non-touching loops. So what must be the other term? So if you go in this way, then suppose if you have more than 4 or 5 or 6 loops, you can say the next term. So this sounds to be similar to the evaluation of a determinant, 1 minus something plus something minus something. So minus the sum of non-touching loops taken 3 at a time, and it goes on like that. Okay, now I'm going to consider another example. It sounds similar to this graph. Now what is the difference? The only difference is you have 2 closed loops, that is one with the transmittance BC, other with the transmittance DE. Okay, now let's start in a different way. Okay, so far we studied 2 terms, that is the forward path gain and as well as the loop gain. Now let us just write down the forward path gain. How many forward path gain you have? Only one forward path. That is, look at this. There can be a signal that starts from x1 and it can reach x6 only in one way. So what is the forward path gain corresponding to that? That will be A, B, D, F, G. Now what are the loop gains? The loop gains are BC as well as DE. And now let's start to find out by back substitution method what is this x1 to x6 to x1. Okay, you know how to do it. Start writing equation from x2. What is x2? x2 is a times x1, a times x1 plus b plus c times x3. Now x3 is b times x2, x4 is equal to d times x3. No, sorry, b x3 is equal to b times x2, plus e times x4, while x4 is d times x3. That's right, x4 is d times x3, and x5 is f times x4, and x6 is g times x5. Now what you need to do is find out x5, substitute here, back substitute, and finally you will get an equation relating x1 and x6, right? And you may just find it out by yourself. Okay, now what you're going to get is x6 by x1. Okay, now look at this. Look at the transfer function. You are going to get a transfer function like this: ABDFG. What is this ABDFG? ABDFG is the forward path gain. So you can write like this: forward path gain divided by 1 minus. What about BC and plus DE? BC and DE are the loop gains, right? So 1 minus loop gain taken one at a time. Okay, so loop gain taken one at a time, and after that, where is the rest? You can't find. Even though there are two loop gains, there is no combination as we find here. Why? The reason is the upcoming terms will be the sum of non-touching loops. Now there are no non-touching loops in the signal flow graph. You have two loops, but they are touching. So that means the rest of the terms are going to be equal to 0. Okay, so this is it. Forward path gain divided by 1 minus the loop gain taken into each valley. Okay, so hope you understood the difference between touching loops and non-touching loops. This is an example of a non-touching loops. Okay, so that means if you proceed in this way, you can frame up an equation, a general equation, to find out the transfer function, and that's going to be the simplest way, and you don't have to go for this back substitution method. And that generalized formula is what is called as Mason's gain formula. Mason's gain formula. Okay, and that's the next section. Okay, now let's move on to Mason's gain formula. So this is actually a easy way of obtaining transfer function from a given signal flow graph, and it is given by the transfer function, and it is denoted by CFS by R of S is equal to sigma k pk into delta k divided by delta. Now, where k is actually the number of forward paths, okay, forward path, while pk is the transmittance or forward path gain. Forward path gain, or it is also called as forward path transmittance. It's not simply transmittance, it is forward path transmittance or forward path gain of the kth path. That means if k is equal to 2, that means you have two forward paths, then you will be having a P1 as well as P2, right? So this P1 and P2 represents what? Represents the this thing, the forward path gain. Now, as in this example, look at this. I have just, okay, I'll draw once again. Say, in this example, if you have a SFG like this, okay, okay. So look at this. So you have a R of S and a C of S. This is C of S. So call this as A, B, C, D, E, and F. So you can say that how many paths you have. So in this problem, k is equal to 2. That means you have one path like this. That is what is a forward path? When a signal is passed from the input node, it comes at the output, and it can come up to that output in two different ways, two or three different ways, or k different ways. Now in this example, this particular signal can come to this side in two different ways, okay, without repetition. So one is say, let us call that as P1, that is a forward path transmittance of this path, that is A, B, C, F. Now another one is A, E, F. So P2 is equal to A, E, F. Hope it's clear. Now, next one is actually, let's talk about delta K later. So let's see what is this delta. Delta is called as the graph determinant. Okay. So, and graph determinant, and this will be equal to, or the expression sounds similar to the evaluation of a determinant. And this is given by 1 minus, okay, 1 minus the sum of all individual loops, okay. Okay, now this is 1 minus sum of all the individual loops. Now I'm going to apply this to example 1. What will be this transfer function? As per this will be 1 minus, what is the sum of all individual loops? How many loops you have? Now how will you evaluate loop gain? The paths that travels, so that when you allow an input to pass through a node, it will reach to that node. So this is a path by which a signal can reach the node. So this is BC. Then you have another one EF. Then you have another one HI. So that means this will be 1 minus the sum of the individual loop gains. That is BC plus EF plus HI. Right? Okay. Now the next one, 1 minus sum of the all individual loops plus the sum of the product of very, very important, product of non-touching loops, right? Non-touching loops. So sum of the product of non-touching loops. So in this example, the non-touching, this is non-touching because the node of this loop, these are the two nodes, right? These are the two nodes associated with this node. While these nodes, these are the two nodes, this won't touch each other. So these three comes under what? Comes under three non-touching loops. So sum of the product of non-touching loops taken two at a time. So what must be this? So this will be plus into, what is the sum of the non-touching loops? These are non-touching, BC, EF and HI. So this will be, now how many combinations? When you take two at a time, that is, you can take BC, EF at a time, BC, HI at a time, and EFHI, so that you will have three combinations, that is BCEF plus BCHI plus EFHI. Am I right? BCHI, BCEF, and EFHI. These are the three combinations when you take two at a time. And then comes again, so it's a determinant. Determinant always having the first term, the second term will be a negative, third term will be positive, and then comes the fourth term. So again it's negative. So what is that? Now I'm going to write this here. This is plus sum of non-touching. Then you have the sum of the product of non-touching loops again. Non-touching loops. Non-touching loops. Non-touching loops taken three at a time. And you can take these three at a time. That means this will be 1 minus BC EF HI. Okay, BC EF HI. So no problem in that. So this is called as a graph determinant. Now, okay, so I hope you understood this. And this continues in this way. The next one will be the sum of the product of non-touching loops taken 4 at a time. Then what will be the next term? It will be minus sum of the product of non-touching loops taken 5 at a time. And it goes on like that. And that is called as a graph determinant, and that is represented by delta. Okay, so you understood what is pk, what is delta, and now we are going into the next one, which is delta k. Now delta k is actually the determinant corresponding to the path pk. That is, it is actually the graph determinant. Delta k is actually the graph determinant of the SFG when the kth path is taken away. Okay, that means, say in this example, what you do is, if I want to find out P1, this is P1, right? What is delta 1? You take away this. So when you take away this forward path, what you're going to get is just a graph like this without any connection. So it's not a loop, no loop, nothing is there. So if there is a loop only, you can write equations like this, sum of all individual loops. There also it is sum of all individual loops without that path k. Okay, so usually it will be 1. So in this case also, this is going to be 1. Now when you consider this P2, what is it? Now take away this. When you take away this node is a part of this loop. So you cannot connect this. When you take away this, you won't be having this node. That means this also is touching that path. So that's it. So that's the graph determinant of SFG, and that is given by delta k. Okay, now coming to this example 2. So can you just find out what is this P1? What is P1? How many paths you have? How many paths? Only one path, right? So k is equal to 1. Now what about the path gain? Path gain will be A, B, D, F, G, I. Just a product of all the individual transmittance of the branch, right? Now, what about how many loops? You have 3 loops, right? L1, L2 and L3. You can call in that label like that. What is L1? L1 is equal to BC, right? BC. L2 is equal to DE, D into E, and L3 is GH, right? Now when you find the transfer function, what will be the transfer function? It will be P1 into delta, A, B, D, F, G, I, that is, that into delta K. And when this path is taken, that is only one path, when this is taken, no loop exists, right? So therefore this will be 1 minus 0, right? So 1 minus the determinant, there are no loops, that means it is equal to delta k is equal to 1, right? Now next comes is 1 minus 1 minus, what about this? These are non-touching loops taken two at a time. So how many non-touching loops you are having? See, BZ and GH, it's a non-touching loop. DE and GH is a non-touching loop. But you cannot take BZ and DE because they are touching loops. So therefore, the equation B will be like this. 1 minus BC into GH, right? Taken two at a time. Sorry, this will be 1 minus the sum of the individual gains. What will be the individual gains? BC plus DE plus GH. Then comes plus, taken two at a time, that will be plus BC, GH plus DE, GH. Can you take BC, DE? No, it's not possible. So this is the transfer function of this example. Okay, so this is how you apply transfer function. Now whatever the complicated block diagram, now the next point is how to convert a block diagram. I have already explained, and we'll start with some examples. We'll start from finding out the transfer function, how to find out the transfer function of a block diagram using SFG or signal flow graph, and by applying Mason's gain formula. Okay, hope you understood what is this Mason's gain formula. Okay, so here you have a block diagram. We are going to find out CFS by RFS. This is the block diagram which we have done in the previous video. So hope you might be remembering that using Mason's gain formula. Mason's gain formula. So in order to apply Mason's gain formula, what you need to do is you need to convert this into SFG. So that's the first step. That is converting the block diagram into SFG, or the SFG of the block diagram. Okay, so you must be very careful to draw the block diagram. Draw the SFG. Now here is the question which we did in the previous video. Okay, this is exactly the same question. We are just trying to do that. Okay, this is not the one. Okay, here is the question which we have done previously, the same question, exactly the same question, and we know the answer. Okay, and hope you all got this as the answer. G1 G2 plus G3 divided by 1 plus G2 H2 plus G1 G2 plus G3. It is into, it's not plus. Hope you might have got like this. Okay, I think it has been mistakenly written as plus. So it is G1 G2 in plus G3 into H2. This is the correct answer. So okay, anyway, I hope you all got this right, and if any clarification required, please inform me regarding this. Okay, anyway, this is what you are going to get by using this canonical form. You will be getting this transfer function. Now what we are going to do is we are going to apply Mason's gain formula, and we need to get exactly the same transfer function which we have already derived. Now we know that, so for applying Mason's, we need SFG. Now SFG starts with the input, so the input signal can be denoted as a node. So this is your RFS. Now you have as it moves, you can encounter a summer. So summer can be represented by another node. Then after that you have another node. It is not necessary that you need to put, because this is also a takeoff point, and one can consider this as a node, and even if it is not considered, there is no problem. Now you have one more another summer after G1, so that can be represented by a node. So that's it, and you can write the transmittance as G1. Then you have one more summer, and in between and between the two summers you have a G2 transmittance. So this summer is also represented. Now the output equation C of S can be denoted as one of the nodes. So this is your C of S, right? Now let's draw the forward. See, you have one more G3 block coming from taking, okay, so it's actually from this. You can draw from this node, right? Now this node, and it comes to this one. So this one is your path, and the transmittance is G3. Transmittance is G3, and it goes on like that. Then from this you have you have a connection, a feedback connection, which is H2, but look at this, you have a negative feedback. That means you need to multiply that by -1, and again you have one more H1 from this side and connecting exactly to that same output, and this is having an H1 but with a negative sign here. Okay, there's a negative sign here, so this must be minus H1. Okay, so this is the SFG of this block diagram. It is, as I repeat once again, you need to change this input point and output point by node. All the summing point has to be replaced by node, and all the blocks are to be replaced by symbol line, and upon which you need to write the transfer function. Then from hereafter you will call this as the transmittance. Now let's move on to the next step. What is gain, Mason's gain formula? That is, the transfer function is given by pk delta k sigma k divided by delta. Now what is k? K is actually the number of forward paths. That is, as one moves from the input side to the output side, there can be different ways by which the input can reach output without any sort of repetition. Then that is, so such a path you can identify as a signal comes over here. It can split into two, right? So this is the arrow. The arrow is very important. Okay. Now this is one of the say signal can come. You can see that it splits. It can split into two. One of the paths can be in this way and reach a CS, and another path is in this way, right? So that means you have k is equal to 2, right? Now once if you identify k is equal to 2, you can find out P1 and P2. What is P1? P1 is the transmittance, the overall transmittance of each path. The path 1, which is G1, G2, right? Now what is P2? P2 is actually equal to G3, right? Now coming to delta, next is we need to find out the loop. In order to find out delta, you need the idea about loops. Now how will you find out loops? Say start from here. You send a signal and see how many paths are there so that that signal will come to that node. Let us look at in this way. Say the signal comes over here and it gets fed back, right? Even if it flows to this, it won't reach here. So the only way by which it reach here is this thing, right? That is G1, G2 and minus H1. So let us consider that as minus G1, G2, H1, right? That's another way. That's the first way. Now another loop, say a signal, it can go in this direction, right? And it can move in this way and come back to this. So what is your L2? The second loop gain is G3H1, that is minus G3H1. And you can have one more loop, say, so the loops coming at the node, originating from this node, is the number of loops is 2, and you don't have any other possibility by which a signal will reach here. Now going into one more step ahead, there is one more possibility, that is you can go in this way, right? So that is minus L3 is actually minus G2H2, right? And sometimes you may feel that a signal coming to this side and come reach over here, that is G2 minus H1 G1, which is already you have written as a, so you don't need to consider that only once. So that's a loop, right? So you have only 3 loops. Okay, so these are the 3 loops, and these are the two forward paths. Now, what is sigma? Sigma is nothing but it is P1 delta 1 plus P2 delta 2. Since k is equal to 2, you have only 2 sum divided by delta. Okay, now let me talk something about, now what is this delta? What is this delta 1? Now delta 1 is actually the graph determinant when you take that P1 away from this graph. Now let us see what happens when this is P1, that is G1, G2. When you take away that path, all the nodes associated with that path also will get removed. Now once when it gets removed, there is no, all these loops, okay, all these loops are touching this path P1, and hence there is no loops which is independent of path 1. Therefore the rest is 1 minus it is actually the number of loops, non-touching loops of this on this path 1. So so this is going to be 1 minus 0, which is equal to 1. Now coming to path 2, that is this path. When you take this path, it will take away these nodes, and obviously we can see that all these loops are having, in some way or other, this is related to this node. If it takes away this node, then these loops have no significance. So therefore, now we come to a conclusion that there are no loops which are non-touching to either of these paths. So therefore its delta 2 is also equal to 1. Now we want one more thing to find out. What is that? 1 minus, right? 1 minus, the first one is the sum of the individual. So 1 minus the sum of the individual loops, right? 1 minus the sum of all individual loops. Now what are the individual loops? This is 1 minus G2H minus G2 G1 G2 H1 minus G3 H1, then minus G2 H2, close the bracket. Then you have plus. Okay, now how many of the loops are touching loops, non-touching loops, that is non-touching with each other? So you cannot take a combination of any of the loops, because as you can see that every loops are touching to each other. Say, I'll just give you an example. Say, what about this G1, G2 and H1? This touches this loop as well as this loop, the loop formed by this path as well as this path. So these are touching loops, so you don't have any more terms. This thing will be 0. That means your delta is going to be 1 plus G1 G2 H1 plus G3 H1 plus G2 H2. Okay, now let us put all these things into this equation. What happens? So your transfer function is equal to G1 G2 plus into delta 1, which is equal to 1, plus P2 is G3 divided by 1 plus, okay, I'm going to take this G2 H2 plus, okay, now, okay, I'm going to take this H1 outside. Okay, so this is equal to G1 G2 plus G3 into H1. Okay, so this is the answer. So I think you might have got this as H1, right? So you may just check. I think it is H1. Just refer your answer. So this is it, G1 G2 plus G3 divided by 1 plus G2 H2 plus G1 G2 plus G3 into H1. So how many steps you have? You have a lot of steps while you do the block diagram reduction technique, right? So instead of that, I have taken this much time because of explanation. Otherwise, it will be taking only few minutes to complete this. So in any case, SFG is the most easiest way by which you can reduce the block diagram and find transfer function. Okay.